everybody in the expo hall. I feel like the exhibitors, they've probably heard me a lot. They're like, it's Gina talking again. Well, you should take a break from your exhibitor booth. Come on over, sit down. We're going to be talking about malaria, and I know a lot of you are going to be interested. We have Dr. Faith. I should have asked your last name.
Osier.
Dr. Faith Osier here, and we're going to be talking about malaria, how to have hopefully vaccination, hopefully get rid of malaria. I'm trying to look up science jokes, but we're going to get right into it. And
Cool.
Welcome to the Sci-Mic stage. Have you ever been here before? Have you ever been to the AAAS meetings?
I haven't. This is my first time. So
Oh, really?
It's really exciting.
Oh,
Yeah.
how are you liking it?
It's very cool.
Yeah.
Very cool.
It's very interdisciplinary. Look, I got
Exactly.
people. Look, they're coming.
Yay.
I know nothing about malaria. I was watching your TED Talk, and you started talking about parasites, and in your first line, I'm already confused because I don't know the difference between like parasites and viruses and what we're actually battling. So can you break down what malaria, like how it actually affects the human body?
Yeah, so malaria is caused by a parasite, and the difference is that it's big. So a parasite, for example, the COVID virus, the virus that causes COVID, it's got about 30 genes. The parasite that causes malaria has about 5,000 genes.
Oh my gosh.
So it's big, for starters. And then it's complex. It's got a complex life cycle. So you get it by being bitten by a mosquito. And then it goes through your skin into your lymphatics. It goes to your liver. And it stays there for about 2 weeks. And then it comes out in your blood.
Oh my gosh.
So when it's in your liver in that stage, you don't know nothing. You don't feel anything. And then when it comes out in your blood, it starts to multiply in your blood, and that's when you begin to start having clinical symptoms. So you have a COVID-like illness, essentially fever, chills, headache, tummy ache. And then if it gets really bad, you might even go into a situation where you need intensive care with coma, convulsions, and severe complications. So while it's in the blood, it forms a different life stage, which are sexual forms. And those sexual forms are bitten. When a mosquito bites you and takes some blood, it takes up those sexual forms. And then those develop in the mosquito, and that completes its life cycle. So it's got stages in the mosquito, and it's got different stages in the human body, and in different organs. And I think one of the difficult things is that it changes as it goes through your system, and the genes that it expresses are different at those different stages. And so one of the reasons why, in comparison to COVID, for example, it's been so hard to vaccinate is just understanding which is the important protein. In COVID, the spike protein is, it's the main protein on the surface of the virus. But for malaria, we've got 5,000 genes. There's so many, and they vary at different stages.
You don't know what to knock out.
So you don't know what the magic bullet is, essentially. Yeah.
In your TED Talk, you were talking about how we've been working on this for 100 years.
Yes.
So can you kind of break down like when we started and what has actually advanced in those 100 years?
Yeah, so I think it's I see it. It's the advances in the molecular characterization of what it is.
Okay.
Because before we didn't know what the proteins were, we didn't know how many they were. So that understanding, those tools to understand which are the genes, where are they, when do these ones come on, when do these ones come off, that's really picked up speed with advances in molecular biology, and that was really in the 2000s that we began to really understand exactly what we were battling. So the tools before that, I think, were kind of rudimentary. That's what people had at the time, but things have advanced. So now we know so much better what we're actually up against.
So what is the current treatment? Like, so you get bitten by a mosquito, you don't know what's happening to your liver, and then you start feeling getting the symptoms. What do you do?
So once you feel the fever, you should take action immediately. And there are drugs that can treat malaria. So most countries, for example, in Africa are using a drug called artemisinin. And they use it in combination with other drugs to try and delay malaria resistance. So you can actually treat malaria. But the problem one of the main problems is that the people that are affected, they live in rural areas that are hard to reach and hard to get to medical services. So what happens is that people start off with homemade remedies and anything local that they can find, and often by the time they come to hospital, they've gotten to a stage where you give them the treatment, you get rid of the parasite, but their body has already taken a downward spiral, so that whatever you do, they don't kind of come back. So I think what's really important is as soon as you're aware, you've got it, but that also brings the problem of diagnosis, because the illness itself is very similar to having a flu, having COVID, having any other so often the mistake is you think, oh, it's just a bit of a bug and I'll get over it, but actually you're progressing deeper and deeper into the disease. So there's a problem of diagnosis, and then actually getting treatment on time.
Wow. Okay.
Yeah.
But your research is focused on the vaccine.
Yeah. So the curious thing is really that in communities where there's lots and lots of malaria, people seem to become resistant to it.
Right.
So if you go into a home, you'll find mom, dad, aunties, aunts, everybody, they have the malaria parasite in their blood, and they're not sick at all.
Asymptomatic.
They're asymptomatic.
Yeah, wow.
But then their little kids living in the same house, they're getting very sick. Sometimes they have the infection too and there's no problem. And other times they have infection and they get really sick and they can die. And so that's what I've been trying to understand is what's the body learning over time that you can just have the infection and be all right. And so that if we could learn that and we could teach the kids to do that, then they wouldn't suffer the consequences of malaria.
Yeah.
Yeah.
And so how is that process going? So you're getting information from people who are asymptomatic. And
yeah. So
next step.
So for the longest time, we were focusing on children because that's who's suffering from malaria. And we were monitoring children over time because, malaria comes in seasons. So when the rainy season starts, there's lots of malaria. So we'd monitor these children over a rainy season, for example, and watch who got malaria and who didn't. And then we'd go to the lab and measure all the sorts of things we measure in the lab to try and tease out what's different between the kids who are getting malaria and those who are not. And so I did that for many years, and it was really hard to see. It was really hard to see, and that's become really more clear now when I've taken a different approach, which is to use a human challenge model.
Okay, what is that?
So that's that sounds bad, but in a human challenge model, what we do is we have volunteers who sign up for a study.
Okay.
We do all the ethical consultation, get all the permissions, etc. And then we infect them with malaria.
Wow.
Using an FDA-approved parasite.
Okay. Working for the government. Okay.
Yeah. So, but the power. It's been really. How can I say? It's like day and night in terms of when we went to look at the immunology. So what we do is we infect these people with malaria.
Uh-huh.
And we go to an area of the country where we know there are people who are resistant to malaria, and then there are others who are not, because they've just not had the infection many times.
Right.
And so when you infect these people with malaria, some of them come down with the sickness, like, oh, I've got a headache, tummy ache, blah, blah, blah. So they get treated and they get out of the study.
And you're there the whole time, so
You're monitoring
right
them,
away.
yeah. But then there are others who are given exactly the same infection, and they just like, yeah, whatever. They play soccer, they watch movies, they're just like, carrying on with their life like
Right.
nothing's happened.
Wow.
And when we looked in their blood, we found for some of them, they just completely cleared the infection. You couldn't even detect it.
Wow.
And we knew that we'd given them, live infection. For others, we could detect the parasite, but the parasite wasn't growing. They were either just like, they just sat on it. It's just like, you're there, but I don't care. And others actually cleared the infection spontaneously. So that was really like living proof, that you can actually get a malaria infection and your body can completely deal with it,
Yeah.
right?
There's some built-in immunity.
There's something that your body knows to do and it can do it.
Wow.
But so now it was, when we did the immunology there, it was much cleaner because we had, we call it a controlled situation. We knew what infection we'd given, when we'd given it, how much we'd given it. The minute they became sick, we'd been monitoring them.
Wow.
So it was much cleaner than the studies I've done like for 20 years. And when we did that, we could see what types of antibodies the people who were clearing the infection had that this other group didn't have.
Right.
So that for me has been a major advance.
And so you're like basically one step closer to that magic bullet.
I think so.
Collection of
Yeah.
proteins that you can kind of target.
Exactly. Yeah.
So the theme of this conference is like science towards, without walls, towards science without walls.
Yes.
In any of this work that you've been doing, was there interdisciplinary work, other barriers that you had to get past towards this advancement?
Yeah, so lots of interdisciplinary work. To carry out what I just described, the human challenge study, that took years of engagement with the community, with policymakers,
Trust.
to build that trust.
Yeah.
So that you could do that. So we did a lot of work with social scientists and really did a lot of preparation because you could imagine the feeling that,
We're going to infect you with malaria.
Exactly. Do you think we're guinea pigs and this kind of thing? So we did a lot of that engagement. And then there's a lot of molecular biology work that we did, in my team to say, okay, now that the genome of the parasite is known and there are all these 5,000 genes, are you going to analyze responses to all these 5,000 genes?
Yeah.
But we decided actually, no, we wouldn't do that. We would take a hypothesis-driven approach where we prioritized genes that we felt these genes are, they code for proteins that are on the surface of the parasite,
Right.
because that's what antibodies can easily see and target,
Right.
So we've done a lot of work to prioritize the proteins that are potentially important, and we'd worked and we put those proteins on a chip so that we could quickly process that data.
Yeah.
So that was
All that chip, it was really cool.
yeah, so that was heavy molecular biology work that came in really handy to
Yeah.
complement the human challenge study. But I think the most important, it's not the most important, another piece was just the immunology.
Yeah.
So when we, normally for immunologists, when we're looking at a virus, for example, like COVID, and we're trying to say, have you made the right antibody response to COVID so that you can get rid of it?
Right.
The test that you do in the lab is like a blocking test. So you're saying, hey, do my antibodies attack the COVID virus and block it from getting into my cells, right? So we have that equivalent in malaria, like, do your antibodies bind to your parasite and stop it from getting into the red cells, which then makes you sick.
Right.
So that's the assay we've been looking at like for 20, 30 years, right? And maybe people did it before me. Well, people definitely did it before me. But what we found was like, hey, that readout wasn't the main readout.
That's not what's happening.
It's happening, but it's not what's the people who are able to control the infection, that's not the main thing they were doing.
Oh, well,
The main thing they were doing was that their antibodies were active on both ends of the antibody. So the antibody is shaped like a fork, right?
Okay.
And on the fork end, that's the side that it recognizes the bad guy and says, "Hey, this isn't a good guy. Let's do something about it." And then on the longer part of the fork, that's the part that it communicates with other immune cells in the body. For example, you've got white cells. For example, you've got molecules in the complement system. And when it does that, it's like activating an army.
Oh, wow.
Because these guys have their own things like cells release the molecules, interferons, or, so they actually, we call them immune effectors, so these are the things that actually kill the parasite.
Oh.
So what we found was that the people who are controlling that infection, their FC antibody function, so the business end of the antibody, was that's where the magic was.
Wow,
it wasn't in the blocking. It wasn't just the blocking.
It was like creating an army, like a
Exactly.
shield.
It's like activating. It's like saying, "Hey, I found a bad guy. Guys, come and help me clear out this infection."
Wow.
Right? But we'd been previously focusing on, hey, just block here on one side, but there's a lot of other activity. And so that was really different, and I think that's, for me, the big advance is that we were looking at the wrong readout, essentially.
You had to have an idea of a new idea.
Exactly.
That's fascinating. I really hope that you get to do more experiments and you get another advance.
Yes.
Thank you for talking to me today.
Cheers. Thank you. Thanks for listening. I hope it was clear.
I was riveted.
Yeah.
Thank you so much.
Cheers.
They're taking notes.